Okay, right. So, hi. This is an opinionated paper which I kind of finish in ironic style, I guess, because we try and do the wrong thing, but maybe wind up doing the right thing, or uh, something. You'll see. You'll see. Right. So, further steps down the wrong path. There's an old Turkish proverb that says something like, no matter how far you've gone down the wrong path, turn back. And I think that's very good advice for life, and I'm going to completely ignore it. Right, so what is bit blasting? So bit blasting is a very popular technique. It's sufficiently popular that people sort of think about it as one of the idiomatic, this is what SMT is. Not really, but and so bit blasting is taking the quantifier-free fragment of bit vector logic and converting it to propositional logic. So when we talk about theory of bit vectors, in this setting, we're basically talking about the theory of integers mod 2 to the n, which of course is a polynomial ring. So yeah, we're actually just mostly, at least the arithmetic fragment of bit vectors, because we also have bit operations like and or, that sort of thing. But often it's rare people mix the arithmetic part and the sort of bitwise parts, unless you do floating point, in which case we do it all over the place. But mostly people don't mix this. So mostly what I'm talking about are quantifier-free fragment of polynomials, multivariate polynomials over integers mod 2 to the n. And because, see what Matthew said at the start about computer arithmetic people and solver people not talking as much as they should, one of the really popular techniques is to take something like this. We've got three 8-bit bit vectors and assertion where we add them up and out and check whether they're equal. It's kind of nonsense, but and they turn it into propositions. And so what you do is for this is an 8-bit bit vector. This is all written in C because the SMT lib was tedious. Yeah, you create 8 new bits for each of them, and then every intermediate value. So when you add things up, you get like, at least you have 8 more bits to represent the output. You also add a load of auxiliary bits to basically represent the circuit structure. And this is what we've got written out here. You've got all of these little clauses. So bit blasting is basically quantifier-free fragment bit vectors, some circuits, propositional logic, feed it in a sat solver, job done. It works. It works terrifyingly, disgustingly well. As someone with the kind of maths background, I feel kind of embarrassed about doing it because it's clearly like, we've got polynomials over like a reasonably well-behaved ring, and we're turning it to a circuit problem. This is insane. So yeah, state of the art. This is the state of the art in tweet form, but if you prefer it slightly more scientific, it's something like this. So what we've got here are the operators that we're using. Here is the, and we assume this is for width n. So this is the number of clauses that we generate. This is the number of auxiliary variables. And this is a property that we might want of our circuit. This is propagation completeness. And what this means is whether if you fix a combination of input or output bits and you use unit propagation, will you find out every other possible consequence of this? It turns out this is a very useful property. If you have propagation completeness across your entire combined circuit, then actually the problem's just polynomial. So this is, you can think of this as like, is this fragment polynomial? And unfortunately it doesn't compose. Yeah, so most of the encodings we use are actually fairly good, right? So a lot of the things that are just moving bits around or negating them are basically free. It just doesn't cost you anything. The bitwise operators are mostly, again, like they're really, really cheap. The modern sat solver, this is not an issue. ITEs have this nice property actually, that the smallest encoding is not propagation complete, but there is a propagation complete encoding which is bigger. We will come back to that. Comparisons, yeah. So the problem is that then, like, most of this is fairly well behaved up until adders. So a few years ago, we wrote a paper where we came up with the optimal circuit for a full adder, and even the optimal circuits for larger adders, and it turns out to be the same thing repeated. The problem is that each time you add up, you can need 14 clauses per bit, and at least n, maybe 2n in some cases, because you want to count the outputs too, 2n auxiliary variables. Now, that doesn't sound like a lot, but believe me, it adds up. Sorry. Yeah, anyway, so then there's this divide, right? And this is what's been kind of troubling me, is that all of these we can do propagate complete. If you put them together in the right way, it's still polynomial, it's all fine. But then you get to multipliers. And yeah, it turns out that multipliers are quadratic in size, which is annoying. And what's worse, they're not even propagation complete. So let's give you an example. So this is pretty much the encoding that CBMC uses when it's bit blasting. So this is long multiplication, right? So what you're doing is you're taking the bits in the left-hand side, you're using it as a mask. So this is the ith bit, you're masking the right-hand side, shift it across and add it on. Simple enough. Unfortunately, you've got n or n minus 1 additions. Each one of those has 14 n extra clauses, and for a reasonably sized multiplier, for something you actually care about, you're already running into the thousands or tens of thousands of clauses. And you don't need too many of those to sync a sat solver. So, right, this is the problem. And this is a compact encoding, right? And if you read the paper that goes with it, I kind of sort of wave my hands a bit and go, well, look, I think, to be honest, the smallest encoding that we're ever going to get for multipliers is going to be n log n. That's the best we'll ever do, unless the conjecture, whose name I've forgotten, about the complexity of multiplication is wrong. What's worse, if you want a propagation complete encoding, it's probably going to be exponential in size. I mean, maybe theoretically there is a pseudo polynomial one, but in practice, like, yeah. So, and we see this in real practice, like, it's very, very easy to generate nonlinear bit vector problems that will just stop every solver in their tracks. Bit blasting, honestly, for dealing with multiplications, I really think it is the wrong way of doing things. Just don't do it. Like, you know, we've got so many good algorithms for working with polynomials. Like, we've got Grosvenor bases. We've got all the exciting stuff about varieties with all the foundations of CAD, and people bit blast stuff. It's just wrong. But see my point, right? I'm going to ignore this, and I'm going to try and make bit blasting a little bit better. Pun again intended. Right, so multiplication by a constant. This is a simple subcase. Okay, so if we say we wanted 975 times x, it looks like this in binary. So, well, obviously we could use that algorithm I showed you, the shift and add. We can be like, okay, well, we're going to need a copy of x shifted by 1, a copy of x shifted by 2, copy of x shifted by 3, not 4, not 5, copy of x 6, 7, 8, 9. Oh God, okay, that's 7 additions. The shifts are free because they're by a constant amount. You just move the wires. But this is going to still be 7 multiplies. Okay. Well, what happens if we not quite factor? I spent a while thinking the answer is factoring, and it's not. But what happens if we realize that actually 975 is 65 times 15? And I mean, you can see it from the bit pattern. Well, what could we do there? Well, if we let y is 15 times x, then the whole thing is just x, and that's shifted across. It's basically saying we can compute those low bits, and oh look, those are the same. We'll just shift them up. Simple. 15. Okay, how do we do 15? Well, 15 is of course famously 16 minus 1. So if we turn that into a shift and a subtract, then suddenly, rather than doing this with 7 additions, we've done it with 2. As 71% reduction. Amazing. Yeah, this works great. Like, I warn you though, this is a nerd sniping problem. If you've got any like particularly precocious undergrads, you want them to be quiet for a little bit. Set them this problem. You have a constant and you wish to multiply by it. You're allowed shifts by a constant, you're allowed additions and subtractions. What's the minimum number of additions and subtractions you need? I spent quite a happy Christmas working on this, just, you know, leisurely, before I found out a few things about the complexity of it. Yeah. So this is the thing, like for 975, it's like, okay, yeah, we can do this, right? This is then really what the problem looks like. People keep on asking me about neural nets, and it's like, okay, just no. But this is part of a convolution neural network. These are floating point multipliers. These are double precision ones. So we've got 4 channels of our convolution. Each one of them appears in 9 different positions. So we have 36 multiplies of every input array element. And those are 106-bit multipliers. So what we really need is not just what's the most compact way of doing multiplication by one constant, but actually we want, here's a set of constants. If you can share subterms between them, even better. And so really what you want is an algorithm that takes in a set of constants and gives you what's the minimum number of additions and subtractions and free shifts needed to produce these multiples. Simple. Yeah, it's MP. I found that out the hard way. So the problem is, what we really want is a scalable algorithm to do this. this is why I say this paper is ironic, because we kind of come back round. Nobody is going to be okay putting an MP algorithm in a bit blaster to go into an MP sat solver. It just doesn't make much sense. So I'm still searching for a really nice approximate algorithm that I can use for things like this, where you've got, 30, 40, 100 different constants that you're multiplying one number by. And what does it minimize? And like the previous one, I mean, I got 71% reduction of that. Once you're talking about blocks of them, I think we can probably get an order of magnitude performance improvement out of this. It's still the wrong way of doing it, but it'll now be 10 times faster. If only I could come up with a suitable algorithm. Yeah. Okay, so let's park that one until I can read a bit more about approximation and approximation theory. So let's consider the general case again. So we're going to consider just multiplying A and B, and we'll get C. Okay. So what? Just humour me to start with, right? What we're going to do is we're going to split each of these up into 4 subwords. And then we're going to come up with these kind of, I call them component polynomials, which the coefficients of which are these. So obviously, if you evaluate P at, I think these were 4 bits in the example. If you evaluate P at 16, you get A back. If you evaluate Q at 16, you get B, right? And then we're going to define R, which is a multiple of them. Cool. So yeah, what this means is that if we know the coefficients of R, we can just shift them across, add them up, job done. It's a linear number of additions. Looks like we're winning, right? If only we knew what the coefficients were. Well, the thing is that we know a few things about polynomials. And one of the fun things we know about polynomials is we know about polynomial interpolation. So if I've got a degree 6 polynomial, if I evaluate it at 7 points, then I have uniquely determined all of the coefficients. So if I make coefficients non-deterministic, all I need to do is satisfy 7 smaller constraints on the evaluation points and add on my big equation, the shifts at the bottom. And I've got to multiply, just like that. And so this is Toombs-Cook multiplication, except you don't need to do the reconstruction step because you can just make these things non-deterministic and it will just work. Yeah. So let's see what this looks like. The nice thing is we get to pick whatever evaluation points we want. So we pick evaluation points that make our lives easy. So we could evaluate a 0. So we therefore know that the lowest coefficient, this one, is of course just equal to the 2 lowest coefficients. Cool. We can evaluate a 1, in which case what we're doing is we're just summing up the coefficients, summing up pairs, then pairwise. We still have a multiply, but this is a much smaller multiply, whereas previously we're doing 16 by 16 multiplies. This is a 4, 5 because of the addition, 6. This is a 6-bit multiply, and remember they're quadratically sized. So just shaving off a few bits, or 10 in this case, makes them a lot smaller. And from one of our earlier papers, we even have optimal multipliers for small things. It's possible to generate them. So then we can evaluate a 1. We could even evaluate a -1, and then we're saving almost all of the terms we've already evaluated, suddenly we need to take the difference rather than the sum. And we can keep on going. We just pick 7 points and bang, we've got the right answer. Except I had a really brilliant student, Kevin, who's credited in the paper, who worked on this, and it turns out there are way more questions than this sort of thing. So what evaluation points do you pick? We think we know, but it feels like there might be a really smart answer. We've just come up with some fairly stupid ones that like keep the whole thing small. What order do we put these into the solver? Because even if we picked a fixed set of evaluation points, we don't have to add all of these constraints immediately. We can add them lazily. It will slowly prune down the space of multipliers. So we've got an incremental encoding for multipliers. Brilliant. This like could save us a lot if only we knew what order to do things in. And this is basically a question about if you've got a system of linear equations, then if you've got enough, you can eliminate. But if you've only got part of a system, can you still eliminate some variables? You can in some circumstances. Then when you think about the fact that, like, say for floating point multiply, you actually care about the high bits, i.e. coefficients d6, d5, d4. If we could pick an order in which to add these constraints so that we get these ones first, that'd be great. It'd be different to what we want for bit vector, but that's okay. We've got questions about how does this recurse, because we've got multiplies, so we could just keep on applying this recursively. At what point do you go insane? At what point should you stop doing it? At the moment, we think the answer is bit width 36, but that might be wrong. And that's just based on at what point you're saving size, as it were. There's a really horrible one, though. Like, we've done this with the component polynomials and the product. And we add them up to get C. But we could also form a component polynomial of C so that we didn't need to do these additions. So we've got the component polynomial of C. What relation does it have with these component polynomials? I think there's something going on there, and it could save us quite a bit, but I don't really know. And again, this is where it becomes kind of ironic, because, I started out going like, hey, we should probably actually use some computer algebra and do these things properly, but let's not do that. Let's just bit blast. And one route I take, I wind up coming full circle and being like, I need to solve an NP problem to solve my NP problem. And the other route I take, I wind up coming back full circle and asking questions about the relations between polynomials over the field, over this ring, which was exactly the question I was avoiding to start with. So that's kind of an ironic place to finish. Bit blasting is the wrong way of handling multiplication. But unfortunately, it's simple, it works, it's popular, it's practical, it's implemented, well optimized, and it's kind of embarrassing that we don't have a better way of doing it. But at the moment, we don't. I kind of hope that SC squared next year, someone will go, look, this is all nonsense. This is the obvious way of doing it. Please. Multiplication by constant. We can really improve it, but we might now have to factor numbers in our conversion to propositional set. which not everyone's happy about. So we need a fast approximate algorithm. Alternatively, we've multiplied by polynomial interpolation. But now that's just kicked up a whole like cloud of exciting algebraic questions about polynomials over bit vectors. Yeah, so maybe I've finished with more questions than I started with. Maybe you also have some questions, he says, as a way to end the talk.
Thanks very much, Martin. I hope we've got time for questions. But Martin, does it, you said you actually include factoring and so on, but isn't that a one-off cost? And you're not factoring very large numbers. So
in the floating point case, I mean, it's yeah, they're not large in the factoring numbers sense. They might only be 100-bit or something. And yeah, it is a one-off cost. So I'm kind of hoping that we might be able to get something like that in, but it's not how people traditionally think of these kind of reductions. So
yes, I realize that, but it's there's difference between, I mean, being NP complete is bad news. Being NP complete in 32 is not actually that bad.
Yeah. So yeah, there's definitely fun to be had there.
Yes.
Yeah.
But at times NP complete in 32, it's a lot better than being NP complete in the whole number of things you're feeding into your bit blasted sat solver.
Yeah. So I mean, maybe at a certain point, what we need to do is actually use the sat solver to compute the optimal layout first, and then generate that. I'm up for it. I'm not sure fellow maintainers would merge that patch, but we'll see.
Yep. Okay. Anyone else got any questions? In that case, Baptiste, pardon.
Yeah, it's still me. Hi, Martin. Yeah, I was thinking, I mean, if you have a multiplication, the context in which you use the multiplication can also help you maybe to restrict what you are interested in. So you could say, oh, I don't care about those bits because anyway, they would be below what I'm interested to. So I mean, it's kind of orthogonal to what you are doing, but are you also investigating this?
I'm very, very interested in it. I just don't exactly know how to integrate it yet. You can throw a lot of stuff away. The polynomial interpolation algorithm works in the general case, but if you want to do it so that actually you don't get the result of the multiplication, you get the result of the multiplication mod 2 to the 16 or whatever, then you can probably leave out, I think you can leave out some evaluation points, but that to me feels like it must have an algebraic expression. I kind of want to mumble something about varieties here, but I don't know for sure. So yeah, it would be, it's a fascinating question, and I'd love to say I knew the answer, but I don't.
Okay, thanks.